Hello, everyone. I am Chao. My talk is Private Everlasting Prediction. This work is with Moni, Naor, Kobbi, Nissim, and Nissim. So in recent years, machine learning has been an important research area in differential privacy. For the learning, there's one basic question. How many examples do we need to learn a good hypothesis? We call it sample complexity. For the pack learning or non-private learning, a well-known result is that VC dimension is a tight bound for the learning task. For the private learning, in general, we know that we can use log C examples to privately learn it. And the log C is always at least VC dimension. But sometimes log C could be much larger than VC dimension. The learning threshold is an example to show that there is a gap between private learning and non-private learning. For the non-private learning, according to the VC theory, we can use constant number of examples to learn thresholds. But for the private learning, both for pure DP and approximate DP, the lower bounds on the sample complexity is depend on the domain size. That is bad because sample complexity grows with domain size. That means it will be difficult to learn thresholds on a large domain. For example, the real number, we cannot learn it on real numbers. So in this work, we try to figure it out. So let's first rethink private learning. For private learning, we get some examples from an underlying distribution and feed them to a learner. The learner will learn a model. And our target is to use this model to predict labels for the new points. And we require that the learner is differentially private. And by the post-processing, the model and the predictions are also differentially private, and we can show them to all people. But sometimes we don't need this model. What we need is actually the predictions. So it is possible that we can hide the model and the learner in a black box and only show these predictions to people. And now we only require to make sure that the predictions are differentially private. And because now we don't leak any information from the model, so it is possible that its performance better than private learning. In the work of DeWalk and Fieldman, they show that we can do that. In their work, they use the label dataset to construct a black box. And we can ask one query to this black box. The black box can reply one high accurate label for us. And the size of the dataset is VC dimension. Combining this result and the composition, we can answer T queries by increasing N to root T times VC. It is much better because now it is independent of the domain size. That means we can do more work with privacy. But now N grows with T. So for a finite size data set, we can only answer finite number of queries. For the machine learning, if we get a model, we can use it to answer any number of queries. So we still need to improve it. In this work, we show that we can predict an unlimited number of queries, and the size of the data set is VC squared. We call it private everlasting prediction. In our general construction, we also use the data set to construct a black box and use it to do the prediction. But the difference is that after the prediction, we will update a new black box and repeat this step. We guarantee that with high probability, every query is answered by a high accurate hypothesis. We can think that for the classical back learning, that is with high probability, we get a high accurate hypothesis, and we use it to answer all the queries. And here, that is similar with 1 minus beta probability. But the difference is that the query could be answered by different hypotheses, but we still guarantee that every query is answered accurately. So it could be an alternative to the learning. For the privacy, we guarantee that it is private for the dataset S and the chosen queries. And this is also an adaptive version of joint differential privacy. So let's see our construction. We separate the prediction into several phases. In each phase, we will store a data set with size of VC in a black box and use this black box to predict VC square queries. And after it, we will construct a new data set and continue to the next phase. For a single data set SI, we can think that it has some privacy budget, and each prediction will use some privacy budget. So VC square queries will exhaust all privacy budget, and we cannot use it anymore. So we need to construct a new data set, and now we have new privacy budget, and that is why it can continue forever. Okay. For the prediction, we separate the data set into some sub-data set, each with size of VC. So we can use a non-private learner to learn a hypothesis from each of sub-data set. Say we have F1 to Ft. And then for one query point X, we use all these Fi to predict labels and do a noisy majority vote on them. So if most hypotheses predict label as 1, then with high probability, the final output should be 1. Otherwise, it should be 0. And for one sensitive information in S, we will have one different sub-data set and one different hypothesis. So we can apply the differentially private mechanism on this set of hypotheses and answer the majority vote queries. In our work, we use between thresholds. It can privately answer adaptively chosen threshold queries. We also need to update the data set. We want that SI and the SI plus 1 are labeled by 2 similar hypotheses. So after the learning, we will get 2 similar hypotheses, and the majority vote will get the similar result. We use label boost to do that. Label boost uses exponential mechanism to select one hypothesis and give labels to all the points. We construct a new data set by the point from the queries. So the sensitive information in SI will not appear in SI plus 1. And the conclusion of label boost can guarantee the accuracy and the privacy of SI plus 1. So in conclusion, we introduced the everlasting prediction, which can be an alternative to private learning. Our setting can predict any concept class with finite VC. For example, the thresholds of the rails. It is a very easy task for pack learning, but it's an impossible task for the private learning. And in our work, it can be predicted with constant number of examples. We leave 2 open questions. One is that could size of S be reduced to linear in VC? Is VC squared in our construction? The second is that could this construction be made in polynomial time? We use exponential mechanism to generate new data set, and it could be time inefficient. Thank you.
It's time for questions. Repeat the question, please.
The question is why we need label boost. Because in our construction we need to generate new data set, and for the new data set we use label boost to give new labels to the query point. Yes. Yes. But issue is that we want that all the labels are given by one hypothesis, because in the classical pack learning, the question is that could we use agnostic learning? Even for agnostic learning, we require that the hypothesis, all the labels are given by one hypothesis. So if we use the output labels, it is possible that it is given by very bad hypothesis. But use label boost, the hypothesis is selected from the concept class. So it can make sure that we can use the pack learning result. In the agnostic learning, the sample complexity is the VC dimension of the concept class or the log of hypothesis class. So we want to avoid this issue.